Okay, fine. So let us start. So this is where we were yesterday, right? We were doing depth first search. Okay, it's called DFS. I didn't write this last time. Breadth first search is BFS. This is called DFS. So we were looking at depth first search, and we looked at the algorithm of how you start with one vertex and keep going by increasing the length of the path for as long as you don't hit a cycle. Then you choose another vertex and continue, right? However, what I told last time was there is a more efficient way to do this when it comes to changing paths, right? So for instance, you started with this pink vertex here, you continued until a pink path could not be extended any further. Then you chose a violet vertex. Which violet vertex should you start with, right? That choice was not clear. So the new path that we wanted to choose once we were stuck, that was also arbitrary. We don't want to make that arbitrary. We want to make that uh, determined. Okay, we want to fix that. So just a small modification over depth first search. Okay, so once again, let me just, I'll show it to you in this diagram itself. So let me just copy this. And okay, so this method is called backtracking. Okay, it is called depth first search with backtracking. Backtracking. Okay, it means you are supposed to track the vertices as you get them. Okay, so once again, just be a little patient. Let me draw that graph. Okay, and I'll show the working example there. So this, this, this. So this is the tree we had. Okay. So what is backtracking? Okay. So once again, the first step is the same. You start with a vertex arbitrarily. Okay. What do we want? We want a spanning tree. Right? And now start with a vertex arbitrarily. So let's again start with this vertex. Start with this vertex. But now what I do is I'll give this a label. Each time I choose a new vertex, I'll give it a successive label. Okay, I'll give it a number. So I'll call this vertex 1. This is the first choice that I made. Is that okay? What do I do next? Depth first search, right? The same thing that I did before. Now among the neighbors, pick one vertex at random, arbitrarily. So let me pick this one. I'll call it 2. Okay. And now remember how depth first search was going. the new vertex that I added, I am looking at its neighbors, only its neighbors, right? So now I'll look at neighbors of 2 and I'll pick one vertex arbitrarily. So let's pick this one, call it 3. Now look at neighbors of 4, pick one without forming a cycle. I have only one choice now. So this is 4. Now look at neighbors and pick one without forming a cycle. Okay. Oh, sorry, I have not been drawing them. So one second. So just give me a second. So this was the first vertex, and then the second vertex, the third vertex, fourth vertex. Is that okay? So I choose one of them without forming a cycle. So let me pick this one and call it 5. So I have added this edge. Okay. Now, okay, let me also keep numbering 1, 2. Okay, so far it's moving the same way as before, but let's continue. Neighbors of 5 without forming a cycle, so 6. Neighbors of 6 without forming a cycle, there's only one choice now, 7. Neighbors of 7 without forming a cycle. Okay, what do I pick? Let's pick this one. 8. Neighbors of 8 without forming a cycle, I don't have a choice. I have only one choice. So I'll pick. Is that okay? Now I'm stuck, right? Now I have to pick one vertex arbitrarily, right? Because I cannot continue this way, right? That is what we were doing. But now I could, last time what I did was I'll pick some vertex. I could have picked this one, or I could have picked this one, or I could have picked this one. Okay, doesn't matter. But now we will fix which is the next vertex to pick. Okay, we will decide in a algorithmic fashion what is the next vertex to pick. So, which is the last vertex we have chosen so far? 9, right? From 9 we cannot go ahead because when we look at its neighbors, they are all included in the list already. There is no new vertex to be added. Okay. So 9 is the last vertex. I cannot proceed ahead. So I will backtrack. Okay. I will backtrack. What does that mean? I'll go one step back. I'll look at 8. Okay. From 9, I go back to 8. Okay. Go back to 8. Now look at neighbors of 8 other than 9. Look at the other neighbors of 8 other than 9. Okay. Are there any? There are no. Okay. 7 is already there. There is no extra neighbor. Backtrack further. Now I am at 7. From 7, now look at its neighbors which have not been included at all. Is there anyone that I can add? Yes, I can. This vertex. I'll call this one to be 10. Okay. So this is 10. Is that clear? Is this much clear? This particular step. Okay. I cannot go any further. So I backtrack. Then I look again. I cannot go any further even now. I again backtrack. At 7, now I can go further in a different direction. Okay, there is a vertex 10 which I can choose without forming cycles. So I'll choose that vertex 10. Okay, that is my new vertex. But now from 10, I will try to go ahead. But once again, I'm stuck here. With 10, I'm not able to go ahead because everything in its neighborhood have been chosen. Right? So I will backtrack now from 10. So I'll backtrack from 10. I'll go back to 7. Everything is chosen. I'll backtrack to 6. Again everything is chosen. I'll backtrack to 5. Again everything is chosen. I'll backtrack to 4. Again everything is chosen. So now I'll remove the arrows. Now you understand what is going on. So I'm not drawing the arrows anymore. So 4, again everything is chosen. Backtrack to 3. Again everything is chosen. Backtrack to 2. Your backtrack to 2. Now if you look at the neighbors, there is one vertex which you can add without forming circles. That will be the new vertex. From 2. Okay, 11. Now I'm not going to backtrack immediately. I'm going to ask, can I go ahead? So from 11, can I go ahead? Yes, I can. There is one vertex I can choose. So I'll go to 12. Right? From 12, can I do? Yes, I can. I can choose one of them. So let me choose one called 13. Now from 13, again, I cannot go ahead because all its neighbors have been chosen. So from 13, I'll have to backtrack now. From 13, I backtrack to 12. Right? Now, from 12, if I look at its neighbors, can I make a choice? Yes, I can. I can choose this one. This is the only one I can. Right? So this is 14. From 14, I go ahead. I can make this choice. So this 15. From 15, can I go ahead? Yes, I can make a choice. So I go here. 16. From 16, I can still go ahead. I can make any choice. So let me make this choice. Let's go 17. From 17, I can make an arbitrary choice. Let's call this 18. From 18, I cannot go ahead. So I backtrack to 17. From 17, I can go ahead in a different direction. So this is 19. From 19, I can go ahead. It's 20. Right? Now from 20, I cannot go ahead. Backtrack to 19. I cannot go ahead. Backtrack to 17. I cannot go ahead. Right? So backtrack to 16. You understand? I'm not going at a branch. I'm just going back as far as I can. Okay. So 20, 19, 17, backtrack to 16. From 16, can I go ahead? Yes. I can choose this one. This is 21. From 21, can I go ahead? Very much I can. Let's go to this one. Let's go to this 22. From 22, yes I can. Let's call this 23. From 23, yes, I only have one choice, but I can. 24. Now from 24, I cannot go ahead anywhere. So 24, I backtrack to 23, backtrack to 22, backtrack 21. From 21, now I can go ahead. From 25. 25, I can go ahead. So this is 26. 26, I can go ahead and make any one choice. I'll make this choice. Let's call this 27. 27, I cannot go ahead. I'll backtrack to 26. From 26, I can go ahead. This becomes 28. Now I'll just do it. 28, any one choice. 29, any one choice. 30, and anything more remaining? No, that's the end of it. Okay, so 26, 28, 29, and 30. And this gives me a spanning tree. Right? Every vertex has been covered. So is this clear, everyone? Depth first search with backtracking. This is all I meant by backtracking. When you finish the scope of extending the length of the path, instead of picking another arbitrary point, you backtrack one by one along that path and try to take a different direction. That's all. That's the only additional rule here. Is that okay? Is that clear to everyone?
Yes.
Yeah. So once again, go through this Uh, in the video, this is anyways getting recorded, so go through the video again, and in the tutorials we'll do many more examples of this, definitely. But yeah, I hope it's clear to you. I mean, I solved a big example, so I hope the idea is now clear to you. Is that okay? So I want to teach another two algorithms today. So look at this for 2 minutes, or take 5 minutes. Okay, look at this for 5 minutes. Just work through the numbers. Now there are numbers also for vertices. We are giving them numbers, so following them should be easier. Look at these numbers. Try to understand what we did once again. Okay, take 5 minutes, and if there is any doubt, ask me. Okay. Is that okay? So this is depth first search with backtracking. Okay. So henceforth, last time what I told you was simply an idea of depth first search, but whenever we do depth first search in problems and all, we will assume that we are doing backtracking. Okay, not the other version that I told you last time. Last time's version was just to make you understand the basic idea. But whenever we apply depth first search, we will always include backtracking. Okay, we will always include backtracking in depth first search. All right. So let's go ahead. So that was that. And today now I want to give you another algorithm once again for spanning tree, but now spanning tree with weights. Okay, that is the idea. Algorithm to find a spanning tree with weights. Is that okay? So, okay. So, what is a weighted graph? So, weighted graph is simply a graph G equal to V comma E. This is the notation you are familiar with, right? V is the set of vertices and E is the set of edges. A graph G equal to V comma E with a weight, let me call that WE, and let's call it greater than or equal to 0 for every edge E in E. Is that clear, everyone? Either you write like this or you write like this, WUV greater than or equal to 0 for every UV in E. Okay, both are the same thing depending on what notation you use, but both are the same thing, right? So WV. Is that okay, everybody? I'm just assigning a weight. Okay, that's all. So let's go back to the previous example again. So not this one, the simpler example. Let's consider this graph, but with weights. Okay, so let me draw it. So let's consider this graph. Okay, now I'm giving this graph edges some weights. Okay, so 2, 3, 1, 5, 7, 4. Is that okay? Every edge is given a weight. Okay. Now what is the question? The question is to find the minimum spanning tree. Minimum with respect to the weight. You understand? There are many spanning trees, right? We have already seen here. So there are several spanning trees. But when you assign weights, okay, the when you assign weights and you only include the edges in a spanning tree, the weight of that is the sum of the weights of the edges. You want to find the spanning tree such that the sum of their weights is the smallest possible. The spanning tree such that the sum of the weights is the smallest possible. Is that okay? So question. Find spanning tree of smallest weight. Okay. So how do we do this? Any idea? Okay, so one way of doing this is what is called Kruskal's algorithm. Kruskal's algorithm. Okay, but how do we do that? I just want you to think about it. I'll give you one simple hint. It is a greedy algorithm. Now you tell me how you will do it. Take 1 or 2 minutes to think and tell me how you will do it. This is the example, okay? This is the particular graph. I don't even want you to tell me in general. It's a greedy algorithm. You want to find minimum weight spanning tree of smallest possible weight in this example. Okay, how will you choose the edges? How will you start? Tell me, give me the first step. What will you do? Ah, oh, okay. I'm going to do it this way. Okay, so yeah, any idea? How will you start? Come on, this should be easy, no? I'm telling you, it's a greedy algorithm.
Sorting करना पड़ेगा पेजेस को
क्या क्या क्या
एक सॉर्ट करना पड़ेगा वे मतलब
क्या करना पड़ेगा? क्या करना पड़ेगा? दोबारा बताओ. हेलो. ग्रीडी एल्गोरिदम का मतलब समझते हो? ग्रीडी एल्गोरिदम देखा है हमने, दो एग्जांपल भी देखते हैं. Minimum weight spanning tree, smallest possible weight among the edges, sum of the edges. So what you do is this. You start with the smallest possible weight edge, which is this edge. I'll choose this edge. Then forget this edge. Look at the remaining edges. Whichever edges remain, I'll choose the next smallest possible edge without forming a cycle. So I can choose this one easily. Now for look at the remaining edges. I'll choose the next possible next edge with least weight without forming a cycle. So I can choose this one easily. It still does not form a cycle. Now look at remaining edges. Next edge of least weight, smallest weight without forming a cycle. 4 I cannot choose because it will form a cycle. It will form a triangle. So I cannot choose 4. So instead I'll choose 5 without forming a cycle. Okay. So I have seen now with this all the vertices have been covered. So the minimal weight spanning tree is this. And the total weight is the sum of this 5 plus 2 plus 3 plus 1. 11. Okay, that is the minimum weight of a spine. Let's do another example. Okay, these are the edges here. Let me mention the weights. So 1, 7, 3, 4, 2. This is 2. 6, 8, 1, 1, 3, 4, 6, 11. So it has 10. This has 9. This has 2. This edge is already given. It's given weight 6, 5. Have we given weights to all edges? Only this one remains. We have 2 and 1. Okay, so we have given weights to all the edges. Okay, we have given weights to all the edges, right? Now, what is a spanning tree? So, first start with an edge with the smallest possible weight. Any one edge with the smallest possible weight. So here the smallest possible weight right now is 1. So let me pick this edge. Okay, first edge is chosen. Next, remaining edges, pick the edge with the smallest possible weight, any one edge. So let me pick this one now. Okay, they don't have to be together, they don't need to share a vertex or anything. Could be from anywhere. Okay, next, once again, pick a vertex with smallest possible weight among the remaining edges without forming cycle. So now again I have 1, so let me take this edge. Okay, once again, look at whatever remains, pick an edge with least possible weight. So now let me choose this one. So if you see, all the edges with weight 1 are now over. Now look at the weights. pick an edge with smallest possible weight. So 2 is there, smallest possible weight now. So I'll pick first this edge. Okay. Then again pick an edge with smallest possible weight without forming cycles. So let me pick this one. I can pick this one. Once again pick an edge with smallest possible weight without forming cycle. Again we have an edge with weight 2. So I'll pick that one. Okay. Now if you see edges with weight 2 are over. Now I have to pick an edge with smallest possible weight from the remaining ones without forming a cycle. Okay, so 3 is there, so let me pick this edge. Okay, once again pick an edge with smallest possible weight without forming a cycle. You see this 3 I cannot make. This 3 if I choose, it forms a cycle along with the remaining pink edges. So that 3 edge I cannot choose. Okay, so remaining edges without forming cycle, what is the smallest possible weight? Now the smallest possible weight is 4. Once again, for weight 4, this edge I cannot choose because that will form a cycle with some of the pink edges. But there is another edge of weight 4 which I can choose without forming a cycle, which is this one. Okay. Now, among the remaining edges, without forming a cycle, choose one edge. Any one. So let's choose the top one. Okay. Now among the remaining edges, choose one without forming a cycle. Again, weight 5, there is this edge, it does not form a cycle even if I include it. So this one is there. Okay. Now again, choose an edge without forming a cycle of minimum weight among the remaining ones. I cannot choose 9, forms a cycle. I cannot choose the curved edge with weight 10, it will form a cycle. I cannot choose the one with weight 11 because 11 followed by 2, 1, 5, 4, 3, that will form a cycle. Okay, this clock go anti-clockwise. 11, 2, 1, 5, 4, 3, that will form a cycle. So 11 is also not there because both the vertices of 11 are chosen, so I cannot choose that. How many vertices are remaining to be covered? Only this one. If you just look at it carefully, only the edge of this 8 is remaining to be covered. So naturally that's the only choice we have now. So among the vertices, among the edges which are not yet chosen, the only smallest possible choice that you can make without forming a cycle is either any one of the edges incident on 8. So let me pick this one. Okay, and that covers all the vertices. Nothing, no vertex remains. So this is a spanning tree with minimum weight. Okay, so what does this spanning tree look like? So if I draw this separately, it's this. That's it. Oh, there is a problem, right? We are getting a cycle somewhere. We're not supposed to get a cycle. I think I made a mistake in it. So let me remove this. Yeah, now it's fine. So let's forget that edge. Okay. Okay, so you get the idea? Just go on adding edges of smallest possible weight without forming a cycle. That's all. That is Kruskal's algorithm. Okay. Alright, so once again look at this. Take 5 minutes, look at this, and tell me if you have any questions before we go to the next algorithm. Okay? Once again look at this, take 5 minutes, and tell me if you have any questions. Is that okay? No questions? Okay, so let's go ahead. The next algorithm is again to find a spanning tree with minimum weight. Okay, just as we saw before. Again to find a spanning tree with minimum weight, but this is slightly different. Okay, so now this is called Prim's algorithm. Or rather, okay. So, any questions so far? You have already seen two algorithms today, so maybe it's not a good idea to do one more algorithm, a new one, because you might get confused. So, so far, is there any questions? If not, I'll stop here and we'll continue tomorrow. So far, any questions? Okay, no questions, then we'll stop. So, breadth first search, depth first search, and Kruskal's algorithm, what was remaining was to give a pseudocode, right? So write a pseudocode for the algorithm. That once again, as we have done before for some other algorithms like sorting algorithms, etc., I will record it in a video and I'll put it up. Okay, I'll put it up on YouTube and I'll share it. So that's it then. So let's meet tomorrow at usual time, 8 o'clock. Okay, let's meet tomorrow at 8 o'clock. Okay, then. Thanks.
Thank you, sir.
Yeah.
Thank you, sir.